Hi everybody, so we're going to do a skill video. This is the first one that I'm doing, and it's very introductory. It is drawing structures in organic chemistry. So quick review, because you should know how this works from Gen Chem already, but a review of Lewis dot structures. There are 6 steps that I go through when I do these, so I just wrote them out here. Count all the valence, draw that least electronegative atom in the center, draw single bonds to the central atom, complete octets, complete the center atom's octet, and then you can figure out what resonance structures are going to be the most contributing. Right, so here's a quick example. Carbonic acid. Go ahead and try this one. And go back to the last slide if you need to. But I'm assuming you've tried it, so there's the amount of electrons that we're working with. Remember, carbon has 4 electrons, and you can find that easily looking in your periodic table. Hydrogen, oxygen, and we're talking about valence electrons here. 24 total valence electrons. And when you end up putting it up here so that everything works out, and everyone has an octet, you end up with this structure. So pretty straightforward. And remember that each bond is represented by 2 electrons. So there's a bond here and there's a bond here. This is, here and here. This is donating a double bond. And this is just a single bond here between these 2. Well, here we go. Same. So this is called a structural formula right here. And you'll see this a lot more in the beginning than you will later on, but it's a good way to start yourself. And honestly, my advice to you is to draw all your hydrogens like this, and also like this. And always draw them out, obviously, with an alcohol. But on your carbons, get in the habit right now of drawing them out so that you get used to it. But, so we have this double bond here with oxygen. Remember that there's 4 electrons in that bond. So the thing about structural formulas, a lot of the time, a lot of people don't include the lone pairs. And you should not fall into that habit. So there should be, of course, 2 lone pairs here, same here. And that'll be important because it will help you with reaction mechanisms later on with arrow pushing. Okay, condensed formulas are a little different. They don't explicitly show the bonds like structural formulas, but they do give a general understanding of where things are connected. So this is a structural formula. It shows explicitly how and where things are connected. So, and here's this, I think this is acetic acid. So the condensed formula then of this guy is CH3, CH3. Notice that this is not the molecular formula, it's the condensed formula. The condensed formula is going to show you more or less how things are put together in the molecule. But remember that a molecular formula would be like this would be C2H6. C2H6, but that would be the molecular formula. The condensed formula shows how things are connected. The CH3, so it's grouped by what is connected onto that carbon. So the carbon has 3 hydrogens onto it, and then it's connected to the next carbon with 3 more hydrogens. So that's why we see these groupings here. So this then, what do you think you would expect? You would expect same thing, a CH3, and then a CO, 2, and then an H. So it's done, condensed formulas are showing you how things are connected by the little groups of substituents. Okay, so next we have bond line structures. So line structures have implicit hydrogens and are the most common way the structures are drawn. So by implicit hydrogens, I'm saying that we're not explicitly drawing them on to the molecule. So here we have the structural formula here. Sorry, and so this is not bond line structure, this is structural. and we're showing everything explicitly, but here is the bond line structure of that same molecule, and there are hydrogens here. There are 3 hydrogens hanging off of this carbon. There's 2 hydrogens here, 2 hydrogens here, etc. But we don't show them because it just makes it easier to draw, and you're going to be drawing a lot of carbon-based molecules, so you do not have to draw out the hydrogens that are attached to the carbons. You do have to draw pretty much everything else though, so you're just exempt from drawing the hydrogens. But just remember that when you're looking at this, every crease has a carbon on it, and every carbon here is neutral. It doesn't have an ionic charge. So you can expect that I would have 4 bonds because it's neutral. So then we know that there's 3 hydrogens here, and we know there's 2 here, and we know there's 2 here, etc. If there was a carbocation and you saw designated by a positive sign right here, or a carbanion, which would be designated by a negative sign, there would be 1 more or 1 less hydrogen. So just keep that in mind. It is implicit, so it's just something to get used to. Really quick, what would the condensed formula be for the structure then? Go ahead and try that. So I'm assuming you've tried it, and it's that. Right, so we're giving a really basic connectivity with this condensed formula. So here's an example that you can try for yourself. So try to do this and try to make it into a condensed formula first. Remember that we're doing groups, right? So start out with the CH3. So I'm assuming you've tried it, and so we have the CH3, and then it's connected to the CH, and then in parentheses we have branches. So we have the CH3, then we have the CH, and anything that's branching off of the parent chain, and the parent chain, remember from naming molecules, is the longest chain. So we have 1, 2, 3, 4, 5, 6 carbons. That's the longest chain. So anything branching off of that is going to be in parentheses. So off of this CH, we have a methyl group. So we have that right here, CH3. Then we have another CH right next to it. And off of it, we have an ethyl, CH2, CH3. So we have that in parentheses as well. And then we have CH2, CH2, CH3. So there, you see that there. So now try and make a bond line drawing of this guy. So I'm sure that you have tried. So we are going to look at that. And there it is. So this is what you're going to be dealing with most often. So another thing that you need to be thinking about is wedges and dashes. So wedges and dashes you will be drawing a lot. And it's basically trying to get at what the molecule looks like in 3D. So here we have a structural formula again of that same molecule. And there we have the bond line drawing. But it doesn't really show you anything that's happening in 3D. So that's where we get the wedge and dash to help us out. And really quickly, I just want to say that this is not how I would draw this. I would actually reverse the wedges and the dashes, and I'll tell you why in a second. But for now, it's fine. Wedges are coming towards you. Dashes are going away from you. And that it will hold true throughout organic chemistry. Now here you can see we're just dealing with hydrogens on the wedges and dashes. You most likely won't need to do that with hydrogens, but it's good practice anyway. You will if there was another atom attached to here, maybe an oxygen or something, then you would need to do this hydrogen here. But so here is the space filling model, and that's what we're trying to get at with the wedges and the dashes. So remember I said a wedge is coming at you. So let's look at carbon 1 here. A wedge is coming at you, so that's this wedge. And a dash is coming away, or is going away from you, and that's the wedge. Same here. There's the, or sorry, that's the dash. Dash is going away from you. Same on carbon 2. This carbon is coming at you, it's a wedge. This hydrogen is coming at you, it's a wedge. And this hydrogen is coming away, or is going away from you, so it's a dash. And same thing for the rest of them. So one thing here that's interesting is this drawing drew out explicitly all the hydrogens, which you don't need to do, but it's helpful. So here we have hydrogens that are not on a wedge or a dash. So why is that? Well, these hydrogens are in the same plane as the rest of the carbons, as the parent chain. So because this hydrogen here is actually in plane with all the carbons, you don't need to put it on a wedge or a dash. And that's pretty obvious, right? Looking at it, all of these are in the same plane. They're not pointing away from you or towards you. But everything else is on a different plane. So how I do these, so I actually reversed this. You can see the C's are backwards, but I always put my wedges to the right and my dashes to the left. And I always do that. And that's my advice to you, is get a system going and stick with it. So my wedges, to me, they go on the right side because that's how the space filling model looks like to me. They go to the right. That's just how I see it in my brain. It just makes more sense. So as long as you are consistent with what you're doing, then you will be fine. But just know that the wedges are coming towards you and the dashes are going away. So another important thing to think about here is how these are drawn. This is the correct way to do them. So they're coming out of the carbon here like a little V. You don't see one hydrogen going this way and one going that way. You won't, so you're not gonna draw it like that. You're not gonna draw the dash up here pointing up and the wedge pointing down. That is incorrect, and you don't want to draw it like that. You want to draw them like this. So why would that be? Well, in the space filling model, you can see that they're situated up, down, and that could possibly have to do with steric hindrance, right? We want to keep the electrons far away from each other. All right. Keep it simple and draw your wedges and dashes consistently, and that is my advice to you. All right, what about double and triple bonds? Well, double bonds do not have free rotation. Single bonds do. So in a model like this, we could totally rotate these bonds around, and it doesn't really matter, right? But this is the lowest energy formation of this molecule because there is less steric hindrance. If we were to rotate this bond up and these two hydrogens were pointing up, there would be a lot of steric hindrance here, so most likely we wouldn't see that conformation, so we'd keep it as simple as possible. And that's why you draw your line and wedge drawings like this as well, in the zigzag form here. It just makes more sense. Okay, so that's something important to remember though, that single bonds do have free rotation, and you will be working with rotating around single bonds, but you won't rotate around a double bond. And also, you won't normally see wedges and dashes on double bonds. And that's because something that is on a double bond is on the same plane as the carbons in the double bond. So any substituents hanging off of that double bond are in the same plane, so you don't necessarily need a wedge or dash on your double bond unless you're changing a point of view. Maybe you're looking this way. Like maybe you're standing here and looking forward. And then you can see that everything would change, right? Substituents on an alkene are in the same plane. I just said that. Triple bonds are drawn at 180 degree angles with the neighboring bonds. So here we are with an alkene. How would we draw that? Well, this one is very particular because we're showing our two groups here coming off the double bond. And there are two ways to draw this. So the important thing here is remember that there is no free rotation around a double bond. So what does that mean? Well, you could have possibly two conformations of this molecule. You could have this conformation where the two bigger groups here are trans from each other, and they're on different sides of the double bond, and that's denoted here with a line and bond drawing, or they could be on the same side. So this is just two conformations, and they are two different molecules. So if we only had an alkane here in a single bond, these would actually have free rotation, and no matter what you did, if you had it looking like this or like this, it would be the same molecule. But because of that double bond, and there's no free rotation, it stays like this, and it makes it different molecules. So here's an alkyne, and you can see that any substituent hanging off of this alkyne here, which is this guy, this ethyl group, that is going to be at a 180 degrees. So the neighboring substituent group, so this guy will be at 180 degrees. If there's something here, likewise. I mean, there is something here. It's a hydrogen. We just don't draw it right because we're doing a bond line drawing. So this is a little bit of a brain teaser. And it's also looking at things that we'll be talking about later on in the class, but pretty soon, so it's something to start thinking about. So knowing that you can make two different kinds of molecules when you have a double bond, try and draw out this 3,7-dimethyl-2,6-octadiene 1-ol, and think about if you could have possibly another conformation of it. So, and I'd like to see two of them, but draw one first and then go from there. So I'm assuming that you have tried. So this would have been the more obvious one to come up with, right? So we have carbon 1, 2, 3, 4, 5, 6, 7. And you notice here you have two double bonds. So then you need to start thinking how the molecule changes when you do rotate this group here, right? Because there's no free rotation, but it could be that this group, connects in a different way, because this name here doesn't say anything about how the groups are connected onto the alkene. And you'll learn more about that later. But so if you got this, that's awesome. That's like way good enough. But the other one that you could have gotten would have been this guy. So here's some food for thought then. Notice that this alkene is different. This whole structure here is a different molecule than this structure. And that's because we changed this group here, hanging off of the first alkene. We didn't do it over here though. So try and think about why. What is the difference between this and this double bond? And if you would like a hint, think about the substituents on each double bond. Are they all different? Are they all the same? What would it look like if you drew out the molecule and you changed it around with this double bond and you flipped this double bond around like we did over here? Would it actually change the molecule? So I'll leave that for you to think about. Later on in the class, we're going to talk about what makes these two alkenes different. So basically, you're looking at the substituent groups, and you're looking on either side of the double bond, and you're asking yourself, what is the higher priority substituent group? And is that on either side, on the left-hand side and the right-hand side? And on here, remember there's a hydrogen here, right? Because we're not giving hydrogens explicitly, but there's no charge on this carbon, so that has to have a hydrogen there because it has to have 4 bonds. Well, that would not be the highest priority group. And we'll go over how to think about priority groups with alkenes. But this big group over here is going to be the priority group on the right-hand side, and this group over here is going to be the priority group, this whole long thing, on this side. So if we look at this alkene, there is no priority group on the left-hand side because they are both the same substituent. There is over here, but there's not over here. So you can't make this alkene different in conformations, but you can with this one because they are different groups on either side. So think about that, and if you want to look into it more, Look up some information about E and Z conformations, trans and cis and trans, and that's in your book, and also easy to look up on the internet.